Imagine a robot sent into a collapsed building after an earthquake. Its mission is clear: find survivors and map the structure so rescue teams can follow. In a perfect world, this robot would build a detailed three-dimensional model of every room, every beam, and every piece of debris. It would calculate the safest path with mathematical precision. It would never waste a second. But in reality, that robot is powered by a battery pack strapped to its back, and that battery is finite. It is running on a computer chip that can get hot enough to burn your hand if you touch it. This simple physical reality creates a massive gap between what the math says should happen and what the hardware can actually do. This is the central tension in modern autonomous exploration. For a long time, engineers relied on a method called frontier-based exploration. Think of it like walking into a dark room and only turning your head to look at the edge of the light you can see. You move toward the boundary between what you know and what you do not know. It is a simple strategy. It works well enough for empty warehouses or clean hallways. But when you introduce complexity, like a forest with uneven terrain or a disaster zone with shifting debris, this myopic approach fails. The robot gets stuck in loops, retracing steps that offer no new information. It wastes energy. It takes too long. To solve this, the field has shifted toward deep reinforcement learning. This is where an artificial intelligence learns by trial and error, much like a child learning to ride a bicycle. Instead of following a rigid set of rules, the system learns policies that balance information gain with travel cost. Recent research has introduced architectures like graph transformers. These systems allow the robot to balance local context with global context. It is like a chess player who does not just look at the immediate threat in front of them, but also considers the state of the entire board. In simulations, these methods have shown efficiency improvements of over 20% in distance and time compared to older baselines. Another approach uses generative adversarial networks combined with transformers to create predictive memory maps. This allows the robot to anticipate environmental changes. It is not just reacting to an obstacle it sees right now. It is predicting where an obstacle might move or where a path might open up. This predictive capability has led to navigation speeds that are 3 to 13 times faster in controlled tests. The idea is to move beyond reactive obstacle avoidance to intelligent navigation in unknown spaces. However, here's the thing that often gets overlooked in the excitement of these breakthroughs. These results are usually achieved in simulated environments running on powerful servers. The simulation is a luxury. The real world is constrained by edge computing limits. When you take a neural network that requires massive compute power and try to run it on a robot's onboard processor, you run into latency and power constraints. The robot needs to make decisions in milliseconds. If the chip has to process a complex graph to update its map, the delay might mean it crashes into a wall before it finishes the calculation. This forces a fundamental trade-off. Engineers must decide whether to have a perfect map that takes too long to update or a good enough map that allows for immediate movement. A highly detailed semantic map might tell the robot that an object is a chair, but calculating that takes time and power. A geometric map just tells the robot there is an obstacle. In a search and rescue scenario, knowing it is a chair is less important than knowing there is a path through the rubble. The hardware reality forces the system to prioritize speed over detail. This is the edge computing constraint that defines the difference between a research paper and a deployed robot. To bridge this gap, the most effective systems are becoming modular and hybrid. They combine geometric mapping with semantic awareness. Imagine a system that uses a standard occupancy grid to navigate quickly but layers a topological graph on top to remember important locations. This allows for continuous semantic updating without needing constant human intervention. The robot can ignore a pile of leaves, but remember that a specific doorway leads to a room of interest. This hybrid approach is critical for large-scale applications where the robot needs to know not just where it is, but what is around it. Despite these advances, a notable knowledge gap persists. We do not fully understand the computational trade-offs between model complexity and real-time deployment on resource-constrained hardware. Just because a lightweight design works in a simulation does not mean it works when the robot is shaking, vibrating, and operating in extreme temperatures. Furthermore, the efficacy of these advanced methods in highly dynamic, unstructured outdoor environments requires further validation. Most tests happen in simulated forests or indoor settings. The real world is far less predictable. There is also a philosophical dimension to this shift. As we move toward fully autonomous, end-to-end systems capable of robust adaptation, we must ask what happens when the human presence is removed entirely. Exploration has traditionally involved a human element, a sense of discovery shared with the operator. When the robot makes complex decisions independently, does the loss of human presence fundamentally alter the nature of the mission? The technology is evolving to replace humans in hazardous or remote environments like space or disaster zones, but the implications of that autonomy are still unfolding. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.